I'm just collecting all the information. So
Oh, okay.
yeah,
Well, good.
uh,
I'm,
this is
I'm
also something that I'm thinking. What is the best thing to do? Do,
gotcha.
because this is not a wallet that a co-op will be promote or anything. So maybe my first idea of creating some tutorial, maybe now it's makes more sense. So
Oh, okay. All right. Well, what you had started and what you're working on is I have a lot of enthusiasm for it. So, I don't want to see anyone put a monkey wrench into or disrupt your development because to see it take shape and move forward it's exciting for me. So, yeah. So, well, good. And thanks for the update on your progress.
uh, the problem is that I put many different stuff in this demo, right? So and this is not related to communication with Arnold and all of these things. So
Okay.
it doesn't make sense that I put all of these things that I didn't test very well, and I'm just testing it. So and
Gotcha.
it's totally unrelated to wallet. So
What you well,
so
it was neat to see someone working on something and being, I think it was, there's the power of a demonstration. When you demo something and a person can engage and do something, it makes it real. So that's what the neat factor was in it. But I understand, you want to focus on, the wallet in that project, and that's tremendous. So, well, good.
yeah, because for a wallet you don't need the server communication because you will not send the private keys or anything to server. So all of this stuff for real-time communications, it's not needed.
Gotcha.
So Ned told me, yeah, it's great, but for a wallet I don't see, any
Gotcha.
use. So,
Yeah. Okay. Well, good. Thanks for the update. How's everybody doing this morning?
Just waking up.
Yeah, it's you're an hour earlier in Austin time, Austin,
Yeah.
Texas.
Yeah,
Cool.
that's right.
Isaac, I'm not even sure where are you located?
I'm in Ohio.
Oh,
Actually,
okay.
it's funny. I live about 15 minutes away from Joshy.
Wow.
Uh, that's funny because I have relatives in Ohio as well.
Hmm.
Joshy lives right on the Lake Erie, and I
That's right.
believe
Yeah.
Langley, Ohio. And I've have visited a town called Sandusky, which is
Yeah.
just to the east of Langley. So I'm generally familiar with the area. So it's a small world.
Yeah.
So
Yeah. We're in Lorraine, but it's like
or
like
Lorraine, yeah.
45 minutes away from Sandusky, I think. I don't
Okay.
go to Sandusky all that much, but I know I'm familiar with the area because that's where Cedar Point is and all of that stuff. So,
Cool.
yeah.
Cool. Well, neat.
Yeah.
And Tomislav, are you in Croatia or where are you located?
in Croatia, yeah, in Zagreb,
Cro-
Croatia.
Oh,
Yeah.
okay. Well, neat. I've heard so much about Croatia and the Balkans and how beautiful that landscape is in the scenery. So that's on my to-do list is someday to visit, those countries over there. So one of these days. Yep.
And you're in
Yeah.
Tampa, right?
Yes.
Yeah.
So, well,
Cool.
actually, right now I'm in St. Petersburg, which is just
Oh,
on the
okay.
other side of the bay.
Yeah.
I'm,
Yeah.
but I kind of go back and forth between St. Petersburg and Tampa. I have relatives in St. Petersburg, and then I go back over to my house in Tampa. So I
Cool.
kind of live on both sides of the bay.
Yeah, I grew up in Fort Lauderdale actually. That's where I grew up. Like all throughout undergrad and everything. That's where I was, and then moved up to Ohio for grad school, and
Cool.
still here. But actually, we're talking about moving to Lexington now, so we might be doing that in the next month or two or so.
Oh, wow.
Mm.
Yeah.
Cool. That'd be a change of scenery for you.
Oh, it'll be great. I mean, we'll be an hour away from like some of the best climbing in the country, so that's one of our biggest things that we're thinking of when we're making that move.
Cool.
Yeah.
Very good. Well, so this is consensus Has anyone have any thoughts on consensus or any topics that they want to go over?
This paper that you posted, Isaac, seems very interesting. But
yeah, did you start reading it? I've only read like maybe the first page. I didn't dig too deep into it, but it sounded pretty cool. I was reading about that Thunder Core. Like I said, I hadn't really heard of that before, but they were talking about their the way that they plan on, like the way that they plan their blockchain sounded to me like they had some sort of like 2-layer thing where they were doing some sort of like practical Byzantine default, like sort of traditional like classical consensus mechanism on one layer, and then they had some sort of like Bitcoin like blockchain on like another layer basically. And they were the way that I understood it was like the first layer was like really fast, but then you get the finality from the second layer. But that's really just my understanding from reading like a short article about it.
And what was that paper, or what was that consensus model?
It's called, well, the project is called Thunder Core.
Thunder Core. Okay.
I'll put the paper in the chat here in 1 second. It is in Discord though, in the consensus channel.
I caught the last few minutes of the Rolang session yesterday, where everyone was talking about the square root mathematics.
Yeah.
So I had sat in on the consensus on Monday and kind of got an introduction to what Greg's thinking was. And I think everyone on the call was still at that time trying to get their head around it. I'll have to go back and listen to the recording of you guys from yesterday to see how much progress you might have made. So,
I mean, we could talk about that if we don't have another topic.
Yeah, I only got like 10 minutes of the recording done, that session.
Oh, yeah. Well, I think we only talked about it for like 5 or 10 minutes, maybe right before the governance meeting started.
Okay. Yeah, I haven't listened to the current RCast, but I believe the current RCast is about the square root. Is that correct?
Yeah. That's
okay.
Right. Yep.
All right. So how many people here on the call have listened to the most recent RCast? Because I have not.
I have.
Yeah.
I was on it.
Yeah. Well, I'm open. The square root or another topic. I'm game for anything.
Yeah, I'm definitely interested to hear that one. Is it even about consensus? Really, all I know about it is it's a square root formula.
Yeah. So I guess the connection to Casper, I don't fully understand, because he was making some sort of connections to Casper and saying that they're different, but they somehow achieve a similar goal because there's like some sort of synchronization that's imposed on multiple validators. And so he was kind of arguing that that's like a form of consensus essentially. He even called one part of it kind of like an anonymous leader election. But here, let me find this slide.
Yeah, I understand that
He's had
this is. Sorry.
Oh no, you good.
This square root is more general than Casper. Casper is doing some other stuff that are more performant, right? Because this square root implies that you run all the choices, or I'm not sure, but you must run something that is not needed in Casper, because Casper has some additional stuff and somehow can conclude something that this protocol doesn't. So and that
Yeah,
right.
I think Casper is doing something more, and like I said, I'm not sure exactly what the distinctions are, but from my understanding, what this square root thing it achieves for us is so we can have n validators or whatever, and then we would be using this concept of like nth root, and we'll have a process that each one of these validators can run to come to consensus on, and we'll only have one actual instance of whatever contract or process it is that these people are all trying to come to consensus on. That's my understanding of it, at least.
And then with the square root aspect, you can start adding on additional features and components, and ultimately you would get something like a Casper. So it's the square root is it's kind of like a bare bones consensus mechanism that you can build upon and start adding components, and you get something more robust. So it's kind of like if you wanted to explore what the world of agreement, and start from a very basic understanding and have limitations and restrictions, a square root algorithm is a good place to start.
Mm-hmm. Yeah. So yeah, show the slides, but yeah, you can go ahead.
He also mentioned that we don't need a blockchain for a square root consensus, right? So yeah, I'm not sure where all this information are stored. How this implies that you store all of the executions, or I'm not sure.
I think this is more of a mathematical representation of what an agreement process would look like. So it's not necessarily something where they're taking this and they want to build something and create something in the physical world. All it is, it's going to stay in this mathematical world, and we're going to look at it and try to understand it and think through it, so we can kind of conclude, aha, yes, consensus and agreement does exist, and this is how, if you follow all of these steps, mathematical steps, you can get to where you want to be. So I think we have Casper consensus, and that's far more robust than what square root is. Casper is something that we're using in the real world, but square root is something to help us validate, to give us assurances that yes, Casper is working in it, and it works the way that it should, because we understand how this world of square root algorithms work. So
yeah, so one of the issues with the square root stuff is you have to kind of assume that everything works perfectly, in the sense that there are no faults whatsoever, right? Because like, if either of these processes is dropped off and like we stop communicating with that node, then we can no longer reproduce the thing that we were trying to reproduce. We would get something completely different. So there's definitely some like idealistic assumptions going on here. Yeah, so that's one of the issues, right? Because like, if I have some process I'm calling square root of p, and I need some other process, square root of p, to run in parallel with it, and I don't have one of those, I can't possibly reproduce the original process.
Yeah, that makes sense. Yeah.
Is the idea here that like p could be some state that you're trying to reach consensus on, and each validator runs one of the two square roots of p?
Yeah, exactly. So you only ever actually produce one copy, kind of like collectively amongst all of the validators. That, like I said, that's my understanding of it. Like, the mechanisms, like how that's actually achieved, I'm not 100% sure, but at least that's the idea.
You don't have any examples?
Oh yeah. There is an example of like a race condition for p, because okay, so I mean that's the idea, right? Is like, with the square root, strictly square root, we need two copies of that thing running in parallel, and then I mean the claim is that we can get this to be bisimilar to the process p, so it'll have the same behavior for all intents and purposes, and then we can do the same exact thing with any positive integer n. We can have the same concept for like an nth root, where we're running n copies of this nth root of p all in parallel, and then essentially reproducing the original process. So that's kind of like the motivation, in a sense, I guess, and the fact that this somehow is saying something about coordination or consensus. But either way, I'm trying to get to the example that we have. So the thing is that it's more or less straightforward unless there are some sort of race conditions going on. And so he'll do it by some sort of like structural induction. And so, I mean, it's, you know, essentially as simple as like just passing the square root to all of the processes or names that you see occurring here. And everything works out very nicely as long as there's no interaction in this par. So like if we're trying to take the square root of two processes in parallel with one another, we can just pass the square root to each one as long as they're not interacting with one another. I'm told that's what this notation means. I've seen this before, but I've never actually seen anybody define it. But
yeah, that's kind of hard.
Yeah, I assume that like there's no possible comm events between P and Q. That's what I'm taking to mean here. Like P doesn't send on any channels that Q receives on. Q doesn't send on any channel that P receives on. I'm assuming is what this means, but like I said, I've never actually seen the definition for it. But that's how he describes it, like no interaction between these two processes. So as long as that's the case, like everything is super easy, straightforward, no issues. But there starts to become an issue if you have some sort of race condition. And so the example that he goes through in the slides is two sends on the same channel competing for one receive on that channel. And so basically what he's doing in this line, I think, is just kind of like naively, what if we just, you know, try to extend that same reasoning and pass the square root to everything individually, then what happens? And so the issue is going to come about when we run this thing. So we're taking the square root. I can't select it somehow. Okay, well, either way, the left side of this equation, we're taking the square root of this race condition. So we just have some process, right? We want to take the square root of it. And ultimately, the goal is we want to take this thing, the square root, run it in parallel with that same exact thing, and we wanted to reproduce what was originally there. However, what starts to happen is when we have two copies of this square root, so taking this right side to be what we're saying the square root should be, we have two possibilities for what gets fed into the receive. So we're basically saying, like, you know, let's think like in this first case, you know, it consumes this square root Q1 message, and in the second case, it consumes this square root of Q2 message. And so now we have sort of an issue because, you know, one part of the network is saying the race condition was settled and the winner was Q1, and one part of the network is saying the race condition was settled and, you know, we got Q2 as the winner for that one. And so, so we don't have any agreement amongst, you know, how the race condition should be reduced.
But isn't that the whole point of reaching consensus on our chain?
Yeah.
For the disputes?
Yeah, well, but ultimately coming to agreement on which is the right one, right? I mean, well, at least I guess that's the point of Casper, right? Is to settle these race conditions and who's the winner of the race conditions. So I guess the point is saying, like, so just thinking about it like this, right? Trying to do like the most naive thing we possibly can just to keep things simple. It doesn't quite work out the way that we want it, because now there's an issue with, we have some validators that are going to say the winner of the race condition was Q1, and some validators are going to say the winner of the race condition was Q2. And so my understanding of the point of this is so that regardless of how you run this process, in the end, we'll produce one result and not have all of these different competing results floating around. Does that make sense?
Yeah.
Yeah, that's good. I have one question.
Yeah.
The word I looked up bisimilar, and I can't seem to get a good explanation of what it is. And I'm probably not clear. Perhaps you could kind of clarify, what does bisimilar actually mean?
Yeah, so it's a relation between processes. It's kind of a general notion. There are many different types of bisimulation, but you know, the way to think about it is it's some way to say that two processes are related to one another, And the real, like the important feature is that we're saying that behaviorally they're like, indistinguishable from one another.
So that was the question. So you have two processes. They're not exact mirrors of one another, but they're
Right.
very similar, and
Yeah.
that they're comparable. So because they're
That's
comparable, they use that bisimilar as the terms. So
Yeah,
okay.
that's right. If you think about it, we have many different notions of relations amongst processes. So like just looking on the syntactic level, we can ask like, are these two processes syntactically the same, right? And then if they're syntactically the same, well, they're literally the same process. Like, of course, they're going to behave in the same way. But we also have this notion of like structural equivalence. And so now we have like, you can reorder pars, you can like get rid of, like stop processes that are in your pars and like some other things.
Mm-hmm.
But if you have two structurally congruent things, they're going to behave in the same way as well. And so bisimilarity is almost like a step back from that, even where we don't even require structural congruence anymore. We're saying like, okay, there's an even like, I guess like coarser notion of this like behavioral equivalence. And like these two
Okay.
processes, if we say they're bisimilar to one another, then behaviorally they are identical, or in terms of like, observable behavior of the processes.
Okay.
Like one plus one.
Basically, there's no way to distinguish them.
Yeah, exactly. For all intents and purposes, they're the same.
Okay. That's what I needed. Okay.
Yeah. And so, there's like a rigorous mathematical definition, but I don't think it's any more enlightening than understanding that like behaviorally they're the same.
Yeah, so it's almost like you have two separate processes. They're kind of constructed, or they look a little bit different, but
Yeah.
essentially the behavior that they achieve, they're
Yeah.
they're the same. So they're essentially copies of each other. So they're
Yeah.
bisimilar. Okay.
And it's not that they're the same as each other, right? It's that they're the same together when paired as p. So it's more like square root of x par square root of y approximates p, because like square root of x could be like ascend on the x channel for nil, and then square root of y could be send on the x channel for nil, and then p would just be send on x nil twice.
Okay. Very good.
I think we can say that 1 plus 1 as a process is bisimilar to 2.
Yeah.
Oh, that's a good example. Okay. That's breaking it down for me. Okay. That was good. Thanks, Tomislav.
Yeah. Yeah. Okay. So that's kind of the setup for the problem, right? Is just taking the most like obvious, like naive route to define the square root for a more complicated process like this. It doesn't really work out the way that we want it, because we won't have all, we won't have the same outcome in all instances. I guess we won't be able to run both of these processes in parallel and then have one outcome. We have it's sort of this like mixing of messages almost. So the way to get around that is to introduce this C process into the definition. I can't highlight anything, unfortunately. But either way, the whole point is like we're still looking at that same expression, right? Like the square root of this race condition, still looking at one receive and two sends all on the same channel. And so now what we're doing is like all of the same stuff. So still the same receive that we had from before. This send is slightly different because now we have this index of L. This send is slightly different. Now we have this index of R. And then the big change is that we're adding this this coordination process, essentially C on the end here. And so the way that I understand this, and I haven't seen this anywhere else except for in this square root idea, is this the superscript L and R. My understanding is it's some way of changing the names. So square root of x raised to the L or raised to the R, those are two different names, and they're also different from square root of x. But he's got some sort of like, like bijection of names where he can just change the names and like keep track of what names are being changed. In such a way that, so my understanding is the reason that we need to do something like this is so we don't have a comma event on just this level alone, right? Because like if we're running two copies of this square root, we don't want them internally, like each copy, to start communicating with itself, if that makes sense, right? So we wouldn't want to do, so something up here, which is even bad already, is before we even run two copies in parallel, we have the chance of, some communication happening here or here, right? I mean, because like we're sending on the same channel as we're receiving on. So we have a possibility for a comma reduction just on the level of one of these square roots, which is not exactly what we're looking for.
Mm-hmm. So C somehow avoids that.
Yeah. So changing these names slightly is going to avoid the comma event on the level of just one square root process, and then the C is going to make sure that these messages are consumed in a consistent way, basically. So like if we have consumption of like Q1 over here, then we'll enforce that we have consumption of Q1 over here as well. So we don't have this like mixing of messages. Yeah.
And does it place an ordering on those processes, or are they still unordered?
Place an order on which processes? The ones that were sending?
Yeah. The two that could possibly be a dispute. Yeah, 2 cents.
Yeah, no, there's no ordering as far as I can tell. So the way that this coordination process works, so he's got the definition here. I mean, it's this long definition. It's basically the whole page. But the point is, this process C is going to be some like joined receive. So it has to consume two messages at the same time. And the point is that it's going to have to consume a message from the square root L channel and also the square root R channel. Well, square root of L and square root X of R. But the thing is, keep in mind, we're going to run two of these square roots together, and then ultimately we want it to come out as like the original thing. So we're consuming two messages at once from the square root of XL and square root of XR. So it could be these two that are consumed in that receive, but it could also be like, square root of XL from this one, and then the other square root process that we're running, we could take the square root of XR message from that one. It doesn't really make any difference because basically what's going to happen is like, whatever those messages are, we're just calling them, little q1, little q2. We don't even use those messages anywhere in this process. So it literally doesn't matter what the messages are. Just the fact of the matter is that we consume from these specific channels, like one from the left channel, one from the right channel.
And then it still sends Q1 in the matches.
Right, exactly. So for each consumption of these two messages, and remember now we're like sending 4, right? Because from each one of the square roots, we have 2 sends that are happening, one on the left channel, one on the right channel. And there will be 2 copies of C as well, right? Because we'll have 2 copies of this process running in parallel. So once we consume all 4 of those sends, we'll have 2 of these out, sends on this out channel, and this out channel is related to the other ones, but it doesn't really matter so much how that relation is. And then what it's going to do is basically like just generate a random number, like 0 or 1, right? And then we have this receive that's waiting for 2 messages on the out channel. So this won't proceed until both of these kind of like coordination processes each have consumed, these messages from the square root channels, and both of these sends on the out channel have actually happened. Does that make sense? Anybody have questions? I know it's confusing. I feel like I'm explaining it in a confusing way.
So there has to be a right to out from two different C processes to proceed.
Yeah, right. Yeah, exactly. Yeah, and so we'll achieve that by the fact that we're running this square root in parallel with itself, right? So we'll have two of these C processes. Once they consume all of the messages that they need to consume on this kind of like top level, then they'll each contribute one of these sends on the out channel. Once we have both sends on the out channel, then we can actually start talking about what's going to happen with this receive, because it needs two messages on out. But basically the point is like each one of those messages on out is just like randomly a 0 or a 1. And if it turns out that they're both zeros, we're just going to pick a certain process. And in this case, it says Q1. But the important thing is that if it picks both zeros, then we're also going to make sure that we send two more zeros on the out channel. Because if you think about it, we have two of these C processes, that are floating around. We've consumed this top level receive. This send on out, those have both been used up to reduce just one of these receives kind of on the inner level. But we still have another receive just like this from the other C process that we're not looking at right now.
Yeah.
Yeah. So then the whole point is like if the first receive got 2 zeros, the second one must get 2 zeros. So we've like enforced a constraint there. If the first receive gets 2 1s, well then the second receive must get 2 1s, and that's kind of the whole point, right? Is like whatever the first one gets, we want to enforce that the second one also gets the same stuff.
Yeah.
So if we have multiple validators running this kind of consensus, they can have different results for rand, right? They can, one validator can decide to have a 0-0 or and the other can 0-1, right? So
yeah, because the order doesn't matter, only the number of zeros and ones.
Well, wait a second though, because so at least the way that I understand it is each validator is only running one instance of this square root process. So they shouldn't have any of this communication. It's only when they combine their powers that all of this stuff starts to happen.
But I mean, you want to, you have this on the left-hand side, right? You have this receive and 2 sends.
Yeah.
And there is a race.
Yeah.
So each validator executes this code.
Yeah.
Right?
Yeah, so I guess the question is like, what has higher precedence? Is it the square root or is it the reduction of the race condition?
Well, I'm thinking that each validator will try to add this C and try to get execute the code, right?
Yeah.
It's or I'm missing something.
Yeah, well, okay, so the way that I'm understanding it is we're not going to resolve the race condition, under the square root, right? We're trying to produce some process that will resolve the race condition in the end, essentially, when we, put everything together. So each validator alone is only going to have access to one copy of C. So they're not going to be able to do this full reduction.
So this is not necessarily something that would actually happen on our chain, right? Like this is like a network level communication.
Yeah. I'm not 100% sure like what the motivation was to come up with all of this stuff. But my understanding is not that we're gonna like, oh well, whatever. We have this other form of consensus now. Like let's just scrap Casper altogether. I don't think that's the intention whatsoever.
But yeah, you can't even look at this contract as being a smart contract because it's not. That would imply that everything that operates on, you've reached consensus on.
Yeah.
But the reality is that each C is is basically just the code that each validator is running.
Yeah. Yeah. And the C is just like imposing a synchronization amongst the validators. It's not saying anything about any one particular validator, I guess, as far as I understand it.
Mm. Okay.
Yeah, it's also interesting about how they send, so the 0, 0 and 1, 1 are for Q1 and 0, 1 and 1, 0 for Q2.
Yeah.
And the order doesn't matter here, it's a par. So if you had 3 separate validators, then you couldn't like use all the different permutations of a bit string of 3 bits. It instead just has to be the number of zeros to the number of ones, right?
Oh.
Yeah, Greg calls this freaks and beasts, right?
Yeah.
That's right.
Yeah.
0, 0 and 1, 1 is like a one thing, and 0, 1 and 1, 0 is another thing.
Yeah, I mean, he had 2 cases here, so he split it, or like two possible outputs, so he split it as like by parity. But I guess with 3, we maybe can come up with some other way to split it into 3 groups that are consistent. But I don't know if it even matters, like what. As long as the probability is the same for both outputs, then I think it's fine.
Yeah, I don't think that you could make it the same with just 3 bits. I just think it grows maybe even more than linearly. I don't really know. But
you're talking about just for like the amount of permutations of all of the bits?
The amount of bits that you'd need for like some number of validators.
Yeah.
Like 3, you might need 4 bits.
Mm-hmm.
But maybe not. Maybe you're just interested in 3 to split this in the like 3 copies, right? 3 parts.
Mm-hmm.
Like just the 2 bits, or
0, 0, 0.
Oh,
maybe
it's kind of interesting because how many combinations of 3 bits do you have? I mean, there's 8, right? There's 2 to the power 3. So how do you split 8 outcomes equally amongst 3 sets?
Well, but you can't just, or you don't get all of them, because you have to consider that 1, 0, 0, 0, 1, 0, and 0, 0, 1 are all equivalent, because you can't assume the order.
Yeah.
Oh, you mean? Oh, yeah.
Yeah.
Oh, right. Yeah, because he's actually matching like a tuple here, right? So this order sort of matters, not really, because like ultimately it just turns into a par, so it doesn't really matter. But
yeah, exactly.
Yeah.
So really, like for 3 bits, you could have 0, 0, 0, 1, 1, 1, and 1, 0, and 2 ones.
Oh, yeah, that's right. I mean, yeah, and one of them you just have, like if there's a single 1, or if there's 2 ones, or if there's 3 or 0, I guess. I'm not really sure if that's,
But then to make it even chances again, there's no way to split it up, so you could have to go to 4 bits.
Yeah.
Well, yeah, I'm not sure how the generalization looks like. Doing the generalization of this specific race condition to like an nth root, I feel like is like fairly straightforward. I think I could figure that out. But I was asking him during the call, like, even if we were to keep the square root and, so still only 2 validators, but now the race condition is like 3 sends amongst, 3 sends, 1 receive. Like, how do we do that race condition? Or like, how do we define the square root in that case? And he claimed that it was straightforward, but I still don't see it. I mean, I haven't thought too much about it after talking to him, but.
Yeah.
We can generate a random number between 0 and 1 and split it into 3 pieces.
Yeah. I don't know. So I think that's more or less the story, at least in this case, right? Is like, so okay, just taking a step back, right? Like, if there's no sort of race condition or something, like you can define this square root fairly straightforward. but once there is a race condition, you have to impose some kind of synchrony constraint to make sure that the race condition is resolved in a consistent way. And I don't even remember what he went to do after this stuff. Oh, I guess he just has like, writing out some of these calculations. That's more or less it. I mean, it's just more like actually writing out the calculations, but that's more or less all that's in here. I think this is like the most important slide for figuring all this stuff out, though.
I wonder how close this could be considered to the Paxos algorithm.
Yeah.
Do you see this like communication between different nodes, like agreeing on a bit almost, or a byte string?
So what does the Paxos algorithm do?
Yeah, it's like the father of all algorithms that use a pre-commit, commit, or prepare, pre-commit, and commit stage.
Okay.
So
this is Leslie Lamport, right?
Yeah, I think so. Yeah.
Okay.
Yeah. So it's just that kind of algorithm that is gonna have all nodes first agree on. And man, it's been a while since I've looked at it, but have all nodes first agree on what they want to commit, and then all nodes see that, and then they acknowledge that they've all seen that, and then the acknowledgement becomes the consensus, I think, which is kind of like this. Because I mean, you have to receive a message from all validators, and then choose something random. And I'm not totally sure. It just kind of seems similar.
Wait, now I'm starting to think that we wouldn't just use bits in a case where there's like 3 things to consider. Maybe you're using like 0, 1, and 2, and then maybe you can have like some equal splitting. But I don't know.
Yeah, that's a good point.
Yeah, I guess you're not constrained to using bits, right? You can use whatever you want.
Yeah.
Yeah, so I don't know. I mean, that's more or less my understanding of the square root stuff. And like I said, I don't exactly see how it compares to Casper. I don't think I know enough about Casper to really see what the differences are and all of that stuff. But like I said, I know the one big difference is that Casper is fault tolerant to some extent. And this is not fault tolerant whatsoever, because if you literally have a single validator that stops participating, then you can no longer produce, the one thing that you were trying to produce.
Everybody halts.
Yeah, right. And that seems not robust enough for mission critical things, but yeah.
They refer to this as radical fault tolerant. So
yeah, it's a pun. Like square root is like radical.
Oh, okay.
Yeah.
Gotcha.
I think Christian even made a remark about how Greg's getting really good with his talk titles, like just making like ridiculous puns in the titles.
That's funny.
Man, he's thought of so many like analogies for how you can think about consensus.
Yeah.
I remember his one on like the predator prey model or evolution, where like currency is the food or something like that.
Yeah, the biological stuff is pretty interesting. He's somehow was saying he can use that and this square root idea together, but I mean, it's like I hardly understand each one like on its by itself, and then they like try and put it together. I'm not sure how anything fits together there, but
yeah.
Yeah, so I don't know if anybody else wanted to talk about things, but I guess that's more or less all I have to say about the square root stuff.
Well, thank you.
Oh yeah,
We
absolutely.
appreciate that.
Thanks. Yeah.
Very much.
Oh, maybe Tomislav, do you want to talk about the matching bug that we found?
The matching bug.
Yeah, the matching
Oh.
bug.
Yeah, this is interesting.
I still have some of that code pretty readily available. I think I could probably show it.
Yeah, sure. If you have it, yeah.
Yeah, sure. Okay. Oh, I mean, maybe we should ask. Like,
Is this
guys-
still part of Casper, or are we moving to computational calc?
I don't know. It's kind of, you could argue it either way, I guess. It's more of a rolling thing or an R node thing.
Yeah.
Yeah, maybe we should move on.
Is that random function new?
Oh, the random function that he uses in the square root stuff.
Yeah, is that part of Rolang, or is he just inventing that there?
Oh yeah, is that part of rolling? I'm probably not the person.
I'm not sure that is part of the roller.
Yeah,
I think it's just
Okay,
creating
that's what I.
random as a yeah.
Yeah,
I think
I think it was just his notation for a random bit, basically.
Right. Okay. Thanks.
He's sort of writing row calc there. It's not really Rolang.
Yeah.
Case
Okay.
structure is not Rolang syntax.
Yeah.
Okay, we'll move on.
All right, cool.